There you go.
So we'll get started. I'll be basically talking about parallel computing using OpenMP and MPI. Uh, uh, it's a long session. I know. I think it's 8 to 11, right, Susan? Right now.
Yes.
Okay.
Sorry, we shocked everybody with this 8 to 12 this morning.
So it should be good. I think from a content point of view, it should be good. It's a long, long day. So let me get started. Let me go to the next slide. Okay. So maybe what I'm going to do is basically start off with kind of the motivation for why we need these approaches for parallel computing. Most modern supercomputers, they've evolved to basically thousands of multi-socket server nodes that are connected with a high performance interconnect. Most of the clusters you'll see will have InfiniBand connections, but there are other high performance networks, like Cray has its own network, and then there are other options. But in most cases, what you'll see is basically a multi-socket server. Within the server, there is non-uniform memory access. And I'll go into the uh, to the architecture of the AMD chip that's on Expanse, and you'll see that in that architecture as well. And usually, usually it's multi-socket, so there's some different speed of communication between the sockets versus going to the memory that's associated with the socket itself. So there's going to be different latencies, different bandwidths, even within a node. And then when you step out of a node, there's the InfiniBand network or whatever high performance network there is. And in most cases, that network is also associated with a particular socket, unless you're having multiple network interfaces on a node that basically hit both sockets, but usually that's not the case. So there's a lot of complexity in terms of how all these processing units, cores are connected between each other and between the nodes, right? And to get good performance on your code, you need to be able to scale within the node, and you need to be able to scale out to hundreds of nodes, if not thousands of nodes. And there's different latencies and different bandwidth involved in the access to all these storage. So the pyramid there is basically showing something that goes all the way from basically registers, which are at a cycle level, and then caches, which are quite fast usually, going out to main memory, which might be on the order of 100 cycles, and then going to remote memory. That could be even slower, and then flash drives and spinning disks. So there's different levels of latency. Where this becomes important is if you're doing something in your code that hits like remote or flash memory or going out to spinning disk, it's going to slow you down a lot. So you might have a really fast clock, but if you can't get your data to the compute in time, it doesn't really help and you lose performance. So you'll see a lot of the optimizations are basically trying to pipeline things so that you keep the CPU busy. So just looking at the AMD EPYC processor, and you might have seen this already this week, but basically there are 8 core complex dies, each of which has 8 cores in it. So you have 64 cores in a chip, and then you have 2 of these chips on the node. So, and then the CCDs are connected essentially through this IO die. So you can see even within a socket, there is a non-uniformity in the memory access. So, I mean, it's high-speed memory, but still compared to cache, it's going to be much slower. So you will see the impact of this if your code is doing a lot of calls out to the main memory, basically. And then the one other thing is the I/O devices, and this includes network, essentially, go through PCI Gen 4. And on expands, the network is associated with one of the sockets, and the other socket has to go through the bridge between the two sockets if it needs to use the network. So that's on the just within the node. But then if you get out of the node, you have all kinds of network topologies. You can have a mesh type setup. You can have a torus. The one on the right where you're seeing those yellow blobs with a torus kind of in all three directions, that is one of our old machines called Gordon that used to have this architecture where it was a 3D torus. And we had two of those 3D torus networks. So we had two connections per node. And each of those yellow blobs there essentially represents 16 compute nodes. So you had 1,000 nodes, but they were connected in this way. So as you can imagine, if you're trying to scale out on this architecture, it will be different from, say, the tree-based architecture that you see below. Now, even in the tree-based, sometimes you have oversubscription between racks, which is what you have on expanse, right? So within a rack, you're on a single switch in expanse. But when you go between racks, the number of connections is not enough to basically do the full bisection bandwidth. So you end up with oversubscription if you're running a job at larger scales than a node. Now, the good news is on expanse, a single rack itself is quite a few cores. It's, I think, 7,000 odd cores. So it's a huge number of cores. But you do have to keep this in mind that when you scale out, there'll be network effects. And then there are other topologies like the Dragonfly network and a few others. But one of the reasons using something like a MPI that is abstracted from this network is basically you might write your code to use particular MPI functions, and you don't have to worry about how that is implemented on the underlying network. So that's the benefit of having a standard like that is you can write your code saying, oh, I need a collective of this kind. And the implementation of that collective will be different on different machines, and it will be optimized for that particular machine. So, that way, you kind of benefit from using a standardized approach. Now, parallel computing basically involves executing instructions concurrently on physical resources. So it's not time slicing. It's more like the problem itself is broken up and run on different cores at the same time, and then you have some coupling between them to solve the whole problem. Now, there are lots of reasons for this. The first thing is capacity. As you know, on expanse, there is a limit on the memory per node. It's 240 gigs. So you end up with 240 gigs and 128 cores. So if you want to scale beyond that, you'll have to go beyond one node, right? So there's that aspect of it. Now, the other thing is expanse has 128 cores, and if your code doesn't scale, then you're not going to get a speed up. Like say you run with one core on expanse and use all the memory, you're not going to be that much faster than your laptop. In fact, like you might be slower because the laptop might be clocking at a higher speed and have a faster memory or whatever. So you really need to actually use all the cores to get the performance out of even a single node, right? So and if you really want to get to petaflops of performance, then you have to scale out to the multiple nodes and to a larger number of node counts. So Now, there is obviously some cost to doing this. There's a lot of coordination of tasks and resources, and also you need to worry about the efficiency of how you're breaking it up, right? Like, say you take a very small problem and try to solve it with 1,000 cores, you might find out that you're spending more time coordinating between the tasks rather than the tasks themselves. And that's where, you have to think about how you want to scale your problem. Sometimes the algorithm might not scale at all, and then you have to find a different way of doing it. So you might see that sometimes the approach might be to use an approach that may take a slightly longer time to say converge, but might be faster in terms of the in terms of the scaling, and do like better scaling, and then overall you might finish in a faster amount of time. So that there's lots of considerations if you start scaling out to lots of nodes. Now there are different execution models involved. There's the shared memory model, where basically all the communication is done via shared memory. So you're not really moving data, you're basically reading off the data from a shared memory segment. So if you're on a single node, this approach will work. But then as soon as you go to a distributed, like more than one node, then you cannot have a shared memory, because the memory on node 2 is not visible to the memory on node 1. So so you'll have to basically have a different model where the tasks are explicitly exchanging messages over the network. So the execution models are also kind of different. So you can have a fork join kind of thing where you're doing threads. So you start off with a serial section of the code and then break up into lots of threads to do like the parallel part, and then join back to serial, and then maybe do another level of threads and so on. Or you could do completely different tasks. You're running the same program, but on different data sets, basically, or pieces of the data. So you're enabling the parallelism by decomposing the work, and this, the tasks will run concurrently. So two different approaches that I'm going to talk about today: OpenMP and MPI. And most modern computers, you'll have to do a hybrid of both of these. But I'm just going to present them separately today. So what's OpenMP? So it's a high-level parallelism that's based on threading. It's quite easy to use because you can start with a serial code and incrementally basically change pieces of it to become parallel. So you can basically take the part of the code that's taking the most time and see if you can make that parallel first, and then kind of work your way backwards into getting a fully parallel code. So you can do this incrementally mainly because it's in a shared memory kind of a setup. Whereas if in an MPI kind of thing, each task will have its own memory segment, and which is not visible to the other tasks. So that's the reason it gets a little difficult, because right from the beginning, you need to be able to take your problem, break it up, and it's not incremental anymore, because once you're doing that breakup, you really have to change the whole code to work that way. But in OpenMP, since you're doing it with a shared memory, you can get away with doing this in an incremental fashion. There is it's an evolving standard, and it's extended out to GPUs now and other accelerators. So you can look at openmp.org for details. What it is a set of compiler directives and some library routines and some environment variables which tell which kind of inform how the directives get used. And then it's supported in C++, and Fortran. So you can pretty much use it in most codes. So the model is basically the process starts single threaded, which is like a master thread, and then forks the child threads in the parallel regions, and then synchronizes back. And basically the overhead is mitigated if you reuse the threads, and the master thread will continue the execution of the serial phases. So the work decomposition itself is done using some programming constructs. There's some scope statements, and you can do declarations in loops. And I'm going to give you some examples of all these. And the mapping to the threads can be static or dynamic. So it depends on what your problem is. Some problems, it's good to just do a static mapping because you can easily divide up the work and it stays that way. But then there are some problems where the workload might differ on different threads, and you don't want to be stuck statically, because then one thread might finish and everything else is waiting, and it just waits for the other ones doing nothing. So then you lose efficiency. Let me quickly check to see if there are any questions. Okay, very good. As I mentioned, the compiler directives are the main mechanism for doing this parallelism. So you can basically have a parallel region and divide the code among threads and distribute loop iteration over threads. You can do specifically serialized parts of the code if they have to be. And you can do some synchronization. So here I have an example of basically how the compiler directive will look like. It just says there's an OpenMP parallel section, and I'll talk about what this default shared and private means, but basically this is the scope of the variables. So in general, this is how all these sections will look. There is a OMP parallel section, and I shouldn't call it. Basically, these directives will decide how the parallelism happens, and then you can also do loops in parallel, and basically sections of the code can be in parallel, and so on. Now, the first thing I want to talk about is the scope of variables. So these clauses determine the scope of the variable. So there are different clauses you can set, like a default clause, which basically means if you don't explicitly say some variable is shared, then or not, like it'll assume this default. Then there's private, first private, shared, last private, and so on. And I'm going to look at some of these clauses. So private means that the variables in the list are private to each thread. And you might need this, right? Like say you broke up your problem into multiple pieces, but maybe you're doing the same summation or something like that in each thread, and then you want to add it later. If you don't make it private, remember it's shared memory, so you'll step on the work from the other thread. So if you don't want that to happen, you can make some of those variables private so that they can't be changed by another thread. If you make the, but then on the flip side, you might want some variables to be shared, right? Like for example, if you're doing advancing some kind of a problem in at a particular time step, or it needs like some particular common variable, you don't want to be initializing that in each thread, right? So you can make it shared and just use it as shared. Just need to be careful that you're not doing some race condition when you're now modifying these shared variables. Default, as I mentioned, is the default scope for the variables. First private basically says the variables are private, but they're initialized according to the value just before the entry into the parallel or working share construct. And last private is the other way around. Basically, they're private, and then the value from the last iteration is copied to the original variable object. And there are all kinds of other things, so you can look at that. And last thing is the reduction basically lets you do reduction on those variables. So this we already kind of looked at the code block. So the number of threads is another thing. This is an important one because by default, if you don't specify it, it might pick up the number of cores on the node and say, oh yeah, I have 128 cores on this node and I'm going to use them all as threads. The problem with that is, say you are trying to do a hybrid case, where you want 8 MPI tasks and maybe you only want 16 threads per task so that you have a total of 128. But if you don't specify anything and it picks up 128, now you have like 16 times 128 threads running on the node, which could be a massive oversubscription and cause problems. So the way it's determined is you can set the number of threads. There's an OMP set num threads library function. There's an OMP num threads environment variable. You can use either one of them to kind of set those. Then there's the part about the work sharing, right? So I told you could split up the work in the loop or basically in a section. And the way you can do that is you can do it statically. So you take the number of loop iterations and just divide it, chunk it as equal as possible. But as I mentioned, that might not be the best thing to do if different loop iterations are taking different amount of time. Then you're going to get an unbalanced situation where a lot of cores will be sitting idle waiting for the others to finish. So in such a case, you might want a dynamic one. So where when a thread finishes a chunk, it gets another chunk. Guided is similar to the dynamic, but the chunk size also is reduced as the work remaining kind of reduces. And then at runtime, you could set this using environment variables, or you can just let the compiler set or compiler or runtime set it automatically. So so we kind of looked at a lot of things that are parts of an OpenMP program. So let's start by looking at a simple program that computes pi. It finds the number of tasks and task IDs, so it gets the OMP get num threads and OMP thread number, and then the pi is actually just being calculated using an integral, and we just break up the integration to kind of do the calculation. So, and we did a simple OpenMP loop parallelization in this code, and it just kind of introduces the concept of private and shared variables. And then in the end, there's a reduction to kind of compute the sum for the final integral. So all of today's examples are basically in this parallel directory that I already copied to all your accounts. So you should have it. If you don't have the parallel directory, you can copy it from this location, but I think all the training accounts should have it already. And we're going to submit a few jobs and see how they go. So let's look at the code. So you can see it's a pretty simple C code, and then there's some variables being defined, the number of intervals and so on. And then there's a pragma OMP parallel num threads comma TID is, we make both of them private. You technically you can make the n threads shared, but the thread ID needs to be private. So I'm setting that to the thread number. And if it's thread number 0, I also run this n threads equals OMP get num threads and print it out. So we just get the number of threads and the thread ID. So that's a simple part of just identifying how many threads we have. But then there is the piece that basically does the integral. So it's 4 over 1 plus x squared that we are integrating. And basically there is a private I comma x, because remember now we are taking this loop and parallelizing it. So if you don't make it private, then you're going to have things stepping on each other. So because this x variable is going to be updated on each of the threads, right? And if it was a shared variable, you would end up maybe thread 2 does part of the calculation and updates it, and then something else overwrites that. Then you're going to basically have a mess with the integration. So we make that private. And the number of intervals, we make it shared, because that's the same across all of them. And we are saying we're going to do a reduction operation on this pi value, right? So we are basically calculating pi this way. So you can run this job by just submitting s batch dash dash res equals SI22 day 5, which is our reservation for today, and pi underscore openmp.sp. So let me see if I actually showed you the script. No. So let me actually look at the script and see. You can see my terminal window, okay, right? Let me just zoom that
We
out.
do see your window, Maya.
Okay, great, thanks. So I'm going to go to the parallel directory. All of you should have this in your home directory, and there's a run underscore commands.txt there, and I uploaded this to the GitHub site too, which basically has all the commands you can cut and paste. So I'm going to just do the first part now. So go to that, and I'm going to submit this job. So let's look at the script so that I can explain what's going on. So these are all very small tasks. So I'm just doing a shared partition because we don't need all 128 cores. I'm just running with 16 cores in this case. The other thing you'll notice is that I'm doing nodes equals 1 and task per node equals 1, and then CPUs per task equals 16. This is the way to do it when you're doing threads. Is the number of tasks is 1, because there's only one main process that gets launched, and everything else is threads, so which are like the task CPUs per task. So that's what you should be doing. This is not so important if you compiled it with just straight OpenMP, but a flag. But if you had a hybrid compilation where you used an MPI compiler with an OpenMP flag, then it's actually bad if you do n task per node equals 16, because it's going to launch 16 MPI tasks, and then the threads are going to be all oversubscribed. Like each of the tasks will be bound to one core, and then you're going to have 16 threads on that core, which is going to be a problem. So you should always match the CPUs per task to the number of OpenMP threads. And once it's run, you should see something like this. Basically, hello from each of the threads, and then just the value of pi at the end. Let's see, go back to this. So that was a simple thing. Oh, I think I have a wrong title here. This is just the pi output. But there are like more work share constructs. As I said, the sections directive, basically the entire section is divided among the threads. There's a work share basically that divides the execution into units of work, each of which is executed once. There's a single directive which basically says execute this with only one thread. You can also make it a master directive which says that the region is executed only by a master thread. There's critical that says you need to take the piece of code that is critical and execute it one thread at a time. Then there are barriers, and then there are wait directives for all the child tasks to finish. And there's an atomic directive which basically says a specific memory location should be updated atomically. That is, not all threads should be able to write it at the same time. So now let's look at a more slightly more complicated problem where we are trying to solve the heat equation. So just the evolution of a temperature profile in 1D. So there's basically a partial derivative in time and a second derivative in x, and you're basically integrating this numerically. So we just discretize it in a very simple way, just approximating the derivative at the first order on the time side and then second order on the spatial side. And the reason I picked this problem is I'm going to show you this problem in OpenMP right now, but then we'll go and do the same thing in MPI, and you'll see why it's easier in OpenMP to do the thing, and then how you'll have to separate things out in MPI. So if you look at the equation, it's again, there is the initial part, which is run only by the master. So this is where I'm doing the master directive that I was talking about. And I'm using exactly 3 threads here, not for any reason that is tied to OpenMP or anything. It's just, I'm going to do the same 3 threads on MPI, and I did 3 threads, 3 tasks there because it's very easy to explain, like the domain decomposition with a visual layout of the grid. That's what I was trying to do. This is not something that you should do normally, that is like fix the number of threads in code. Like it needs to be kind of a variable that you can set explicitly outside of the code domain, basically. So the code, we just initialize the temperature. It's a sine curve that we are initializing it with. And then we are iterating for 3 steps. So you do a loop, basically parallelize the loop. The private part is the global variable there. And actually that wouldn't have mattered, I think, but anyway, we are and then the shared part is basically all the temperature, the alpha, the delta x, delta t, and time. So it just takes this loop and parallelizes it, essentially. And then we write the solution out. So there's another script, heat underscore openmp.sp. You can run this, but it's simple enough to submit the job and look at it. But I'm going to skip submitting that from my account. So you see the sample output, you just get 3 iterations and then the solution that gets printed out. Just remember this when we get to the MPI part. So remember here, it was a very simple thing, right? This is really the only thing that's different from the C code that would have been serial. Like the serial code would have done this loop without these pragmas. That's it, right? So you just added this and it became parallel. Now we'll look at it on the MPI side later. So there are some runtime libraries in OpenMP that let you set and query the number of threads. Oh, I heard something. Usually that is a question. Let's see. Oh, there's a question about why there is an OpenMP barrier. It's to just synchronize across all the tasks if you want all of them to kind of wait for everything to finish. This is kind of needed if you're doing loops, because you like here, for example, you had the time steps. You don't want to end up on different time steps on different threads, right? So you want to have a barrier to kind of synchronize everything. So let me go back here. So the runtime library routines, setting and querying the number of threads, there are routines for that. You can do the thread identifier, we saw that. We can also set like the dynamic threads feature using a library. You can do nested parallelism. You can do locks, and also you can basically query the wall clock time and so on. So there are some routines for doing these tasks, and some of these can be done using environment variables, which is what is on the next slide. So you can do the OMP schedule, OMP num threads, OMP dynamic true or false, OMP proc bind. This is an important one because it binds the threads. This may not look important in terms of, oh, wow, how does it matter if the thread is moving around? But remember, all our memory layouts are kind of non-uniform access, right? So imagine on expanse, if you had the whole node, but you were using, say, 18 threads, 16 threads and 8 tasks, and you let the 16 threads wander, then you could end up in a situation where some of the threads end up on the other socket, and then your memory latencies and your memory access is going to be a lot slower, and you'll lose performance. So you want to bind the task to the threads as much as to each location as much as possible, so that they don't move around during the run, basically. So if it allocates memory locally, then it'll stay local and scale better, basically. There's also the OMP stack size. This is the size of the stack for the threads. That becomes an issue if you're basically initializing a lot of variables on the stack, and it's not enough. The default is not enough, so you can change that. Some general considerations of OpenMP performance. One thing is minimize the use of barrier, critical, and ordered regions. Basically, all of these mean that threads will wait for the other threads. Like they won't run in parallel. So if you have a big section that is doing this sort of stuff, you might end up with a poorly scaling code. And parallelize at a high level, maximize the work in the parallel region to reduce the overheads. Use the right loop scheduling, like as I mentioned, depending on how your workload is, like say the one that we just did where the loop is kind of doing the same amount of work at every step, you can just do a static decomposition. But if you had a situation where some parts of it take longer than other parts because you have some random component that decides how much time you might end up spending in a particular region, then you can have a very unbalanced situation. You want a dynamic or guided kind of scheduling. The last line there is avoid fault sharing, and then I'm going to talk about that in a little bit detail. So what is fault sharing? A lot of the modern processors have cache buffers between the slow memory and the high-speed registers of the CPU. You saw that in the architecture for the CPU, right? Now, when you access a memory location, it doesn't just load the one memory location. It causes a cache line to be copied into the cache. Now, in an OpenMP code, two processors might end up accessing two different elements in the same cache line. Now, this is fine if you're reading the data, but if you write to the data, what will happen is this will, like one of them will write and the cache line will get marked invalid because you have to be coherent across all of them. So then the whole cache line will go out to main memory and you have to reread it. And that can lead to a huge amount of memory traffic, even though the write is not to the same element. It's to different elements, but it's basically in the same cache line, which is why it's called fault sharing, because it's not actually doing to the same element. But what it does is increases a lot of traffic out of your cache to the main memory, and that can have a huge performance impact, especially if this is in a loop. And there's a lot of info on this in this link on the Intel site, and also this YouTube video. You can take a look at it. And it's quite easy to do because Because if you have like an array and then you're updating it, if that is if the array is like larger than I mean, is basically being split up into multiple threads, you could end up with parts of it on the same cache line, and you end up with a fault sharing. So there are lots of options of avoiding this. There are compiler directives which basically align the variables on a cache line boundary. You can pad these arrays so that the array elements begin on the cache line boundary. Or you can just do thread local copies of data, assuming that the copy overhead is small compared to the overall runtime. I just have this homework slide. You don't have to do it, but you can go poke around. The one thing I want to mention is that the Livermore tutorial that I have linked here, and I have the link at the end too. You can go there because basically they have a lot more detail on both OpenMP and MPI. These are really nice tutorials with a lot of information. Like they are full day tutorials. We are doing the content in like half an hour. I mean, 1.5 hours, what it should be like at a full day level. So you can go take a look for all the details. And you can take this particular example and try to figure out how to do the various scheduling and environment variables and see how much is going on. So that's basically the OpenMP part of it. I'll do a little bit of MPI and then we can take maybe a 10-minute break, I think. All of what we looked at so far is shared memory on a single node, right? But if you need to go multiple node, you have to do MPI. Now you can do MPI within a node too. There's no issue doing that. In fact, a lot of codes might do better with MPI even on a single node, just because of the overheads and all the issues that we were seeing with the fault sharing and those sort of things. You can sort of avoid some of those issues with MPI. It's a low-level message passing abstraction. So basically, the same code runs everywhere, but depending on which task it is, you can work on different parts of the data. It's designed for distributed memory, but you can, as I said, you can do it on a single node. Also, you can combine MPI with OpenMP. It's a specification, it's portable, so it's kind of a de facto standard for parallel computing. There are lots of implementations of this. So there's MVAPICH2, which used to be the default on Comet. On Expanse, we didn't set a default because we figured out that a lot of applications, there wasn't one single MPI that was doing well on all of them. Like we kind of have to use different ones for different codes. So we didn't put a default in. There's Intel MPI and there's OpenMPI. Pretty much high performance implementations are available on any interconnect and system. Even the specialized machines like the Craze will have a MPI implementation that's specific to their machine that is very performant. And there's a lot of different types of communication you can do. You can do point-to-point, that is one task talking to one other task, or you can do collective where all the tasks are talking to each other, basically sending data to each other. And you can also have various data types. And there's parallel IO, there's tools to basically look at the performance, and there's also one-sided communication, lots of different things you can do. So what are the typical things in an MPI code? So you have, usually you start with an MPI include file, which has some of the definitions of all these functions and variables. And after the include file, you can basically do your normal declarations, and then do an MPI initialization. Once the MPI init happens, it's basically the parallel code from there on. Now remember, in MPI, what will happen? So in OpenMP, you had one process and then a bunch of threads being spawned, right? In MPI, when you start launch an MPI job, it will just launch like if you different number of tasks. So say if you say I want 16 tasks, it's going to launch 16 different processes, even if it's on the same node. And each process will have its own memory, which the other tasks don't see. It's going to have the same variables and definitions, all private to that task, right? So the other task has no idea that what's on the remaining tasks. So so the same code runs within each task. It's just that you do know the MPI rank, so you'll know which process you're on, right, in each task. So it's your job to basically write code that does different things based on this rank. So basically, say if you launch 16 tasks, you will have one task ID that goes from 0 to 15, and then you have to divide up, say, oh, task 0 should be doing this piece of the work, task 1 should be doing this piece of the work, and so on. You have to explicitly do that. There's no automatic thing that can do it. Like, whereas on the OpenMP side, remember, you could take a do loop and say parallelize this, and it's going to just do that piece, right? But here you're explicitly going to write code that does different things based on what the ID is. And then you can communicate between the processes during the parallel section, and you can do some communication, exchange information, and then continue the parallel code and then communicate again and so on. And then I explain this with the heat equation a little bit later. You'll kind of understand what I mean by this. So we'll start again with a simple program that compiles pi. Same thing we were doing before. And find the number of tasks and task IDs, calculate the pi using the integral, and at the end of the code, you're basically summing all of it and using a collective reduction operation. So basically the same thing we were doing before in the OpenMP code. But you'll see it's a little different in terms of how the code looks. So you have include statements, like I was saying, the mpi.h. You have the initialization, I mean, the variable definitions, and then you have the MPI init, which says, okay, this is an MPI code. The MPI com size actually tells you the number of processors, and the MPI com rank tells you the rank of the particular task, right? And then there are barriers in MPI too, where you can basically wait for all the tasks. But anyway, in this case, we write it out. Now, you can already see there's a difference, right? Basically, if you look at the initialization piece on the OpenMP case, we just initialized it with a loop, right? Because basically the shared memory. Here, the thing is, every processor will run the same code, right? So if you start the loop from 0 to some number of intervals divided by the number of processors, you're going to run the same loop variable on all of them. So say you had 128,000 as the number of intervals, and you're running with, say, 4 processes. Your loop will go from 0 to 32,000 on all 4 tasks. So it's your job to figure out, hey, if I'm on processor 0, I should be looking at this range. And if it's on processor 1, it's a different range. The way we are doing that is we are defining a global variable which is based on the rank of the process, so that you're doing different parts of the integral on different nodes. And even the initialization is different. So for example, If you're on the second task, the rank will be 1 because the rank starts from 0. So the second task will have a rank of 1. And notice I have this local interval, which is, as I mentioned, like if you divide by 4, if it was 4 tasks, you would have 32,000. So then this would be like 32,000 plus I, right? So the I is still going from 0, but then on rank 1, you're going to go from 32,000 to 64,000. And rank 2, it will be 64 to 96 and so on. So this global variable is telling you, which piece of the integral you're doing. So the X value that I'm calculating is now based on this global, so that I'm basically picking out the right part of the integral to do on this task. So you calculate the 4 over 1 plus x square again. Now, this local pi is going to be local to each task. So then you have to explicitly do a reduction operation. This is another function call, which basically takes the local pi and does basically an MPI sum on all the tasks and then puts it in this pi variable. And that's what we output in the end. So it's a little different from OpenMP in the sense you have to explicitly break up the work by telling it exactly what piece of the work is being done in each task. Okay. So some of the main parts of the code, the initial MPI init, this has to be called once in every MPI program before you do any other MPI functions. MPI com size returns the total number of tasks in a communicator. MPI uses the communicator to define which collections of processes can communicate with each other. And then the default MPI com world includes all the processes. The user-defined communicators are kind of also an option, but by default, most codes will be using MPI com world, unless you have some really fancy thing you want to do with the communicators. One situation scenario in which this happens is sometimes codes will, like if you have a lot of tasks, like say you're running with 64,000 tasks, which some codes do. Some codes are scalable enough that you can go to huge core counts. You don't want to be writing from 64,000 cores. That could be a huge problem because it might overwhelm your parallel file system if that many writes are going out simultaneously. So you might write, you might have some tasks that are dedicated to just doing the I/O, and you might have them in a different communicator, for example. So there are cases where this is needed, but most codes you'll be doing one communicator. And then the com rank just returns the ID of the process within the communicator. And once you do finalize basically the MPI ends. The other routine in this code was the MPI reduce, which is a collective, and we'll have some examples of this later in the talk. So let's go and do this piece of compiling and running the MPI code. And so I'm going to go to I think it is the simple directory, and the run commands are there. So you can basically do module reset, module load GCC, and module load GCC and mbap h2. So mbap h2 is one of the MPI flavors that's available on Expanse. So let's compile the code now. And I'm going to submit the job and then look at the script. So in this case, now you see that I'm doing nodes equals 1 and task per node is 16, because now it's 16 different tasks, right? So that's what that is. And then for MPI launching, we are using srun. There are other mechanisms to launch this, but srun is integrated with Slurm, so that kind of works well. So srun -- MPI equals PMI2. So Slurm has different PMI interfaces. We just use PMI2. You can use PMI-X if your MPI is enabled with that and so on, but there are different options. But anyway, what this will do is launch 16 tasks, and again, you get a hello from each task and the value of pi. So now I'm going to kind of go a little bit deeper into each of the communication types and how you can pass data and so on. So starting off with point-to-point communication, this is basically if you're passing data between two and only two different MPI tasks. So say you're going from task 2 to task 4, for example. So typically one task will do a send and the other will perform a matching receive. The send operations have choices with different synchronization and buffering options. Basically, when is a send considered to be complete, and when is a send, or where does the data sit when till it's received, and so on. And any type of send routine can be paired with any type of receive routines. MPI also has some routines to kind of probe the status of the messages and some wait routines that are associated with that. So let's look at some of the examples. So basically, if buffer space is MPI buffer space is used for data that's in transit, whether it's waiting for a receive to be ready or if there are lots of sends and going to the same task, receive tasks and so on. The system buffer area is managed by the MPI library. So the user really doesn't need to know about this. I'm just showing you how it works, that's all. And it can exist on both the sending and receiving side. There is an option for user managed send buffer also if needed, but most of the time you don't need to worry about this and it's done by the MPI. So there are different send and receive options as I was mentioning. I'll start with a blocking send and receive routine. So the blocking send call will return when it's safe for the application send data to be reused. So this can happen as soon as the data is copied into the system buffer on the receive process, right? So basically what this means is, like say you're doing a lot of updates on the, I mean, you will obviously be doing a lot of these codes will be doing iterative things, and you might send something and then want to do more computations, right? So the send call will return as soon as the data is copied to the system buffer on the receive process. And it's synchronized if there's confirmation of the safe send. Now the blocking receive returns once the data is in the application buffer and can be used by the application. So it needs to be out of the system buffer basically. So the blocking send receive example is out here. So here, basically, I'm saying if the task ID is 0, send something, and if the task ID is 1, you receive something. So I put a break here. Let's see. Yeah, I think we can take a break now for like maybe 15 minutes and then come back. It's a good time to stop, I think. So Susan, you want to pause the recording? Or?
You're on.
Thanks. So let's continue on. So basically, if you submit this blocking.exe file using the submit script, you'll see that basically the buffer gets sent and you see what gets received. Now, one thing that can happen if you have these blocking sends and receives, that it's pretty easy to deadlock processes that are just waiting on each other. For example, if you basically do a synchronous send, which waits for the confirmation of the receipt from process 0, and then have another send from processor 1, and both the receives are after the sends, they'll not complete because they'll be just waiting for the receive to post for both of them. And it'll never get to those because the send is blocking them. I mean, this is a very simplified example, but this can happen in a subtle way if you're writing some big code and don't realize that this is the case. So like I have an example called deadlock.c. So you can take a look at that. Let me pop the thing up. So all it's doing is has a send buffer, a receive buffer, 10 elements, and we are sending synchronous sending data from task 0 and task 1, and then the receives are after that. So to compile any MPI code, just use the MPI wrapper. So one thing I want to say is, so right now we are doing it with GCC, right? So if you do MPI CC dash help or sorry, dash version or dash version, you can see that the underlying compiler is a GCC compiler because that's what we compiled this with. But so all of the GCC options will be basically present. So if you have an Intel compiler underlying it, you'll see the Intel compiler options. But in any case, so let's compile it. Compile the code using this one. So that's done. There's a warning you can ignore and submit it. And you'll see that it'll just sit there and not finish. And I deliberately, if you look at the batch script, I made it quite short in terms of the request. Basically ask for only 1 minute so that it doesn't sit there for a long time. So if you had put 48 hours there, it would just sit there for 48 hours. So you'll see it's about 27 seconds in. It's in a little bit it should time out, and then you'll see an error like this. Slurm will basically kill the job because I had the time limit set to 1 minute, right? So srun will get killed, and then Slurm will basically have the message saying it's canceled at this due to time limit. But remember, this is not being killed by MPI, it's being killed by Slurm that's outside of MPI. So, I mean, there are lots of ways to fix it. One simple thing is to just reverse the order on one of these things, right? Like if you put on the second process, if you put the receive first and then put the synchronous send, then what will happen is the first process will do the send, this receive will post and go to the send, and then the other receive will post. So then it'll be not deadlocking anymore, and we can just do a quick. So this one finished. Finished in the sense it got killed. So you'll see canceled due to time limit, like I was saying. Now, if you look at the run commands, let's go down to the first fix. So do that. And basically submit the batch job. And since we are in a reservation, this will finish instantly. And you see the 10 elements that got sent. So that's good. So that's one fix. But there are other things you can do, actually. There are lots of non-blocking options in the send receives. And there are other reasons for doing non-blocking, and I'll talk about that. So the non-blocking MPI send receive routines, the receive routines will return before there's any confirmation of receives or completion or anything. So the routines will just put in the request and return, right? Now, obviously there has to be some corresponding thing that checks on these. So there's an MPI wait routine that can be used to check the status. And it blocked till the operation is complete. Now you might be thinking, okay, well, if I'm putting a check routine after that, won't it just sit there? But the trick is that if you do the send and you can do other work in the meantime, you can then overlap the computations and communication. This allows you to scale to really large core counts because your communication is essentially hidden. And the simplest example of this would be like if you had say, a domain that you're solving the parallel, like remember the heat equation, we were breaking it up into different domains and solving pieces of it on different tasks. So what you could do is do the boundary points first and do a non-blocking send receive, and then continue on and do the rest of the points in the domain that don't need any information from the neighboring tasks next, and then go back and check if the original send receive got finished, and then go on to the next time step. What that does is basically if your domain is large and your boundary is small, like usually that's the case, right? Like if you have a 3-dimensional grid, your boundary is going to be a plane, 2D plane, but your grid is going to be a 3-dimensional grid. So if you have a lot of points in the 3D grid, you will have a lot of work to do while the boundary is being transferred. So you can overlap it beautifully and basically scale out. As long as your problem is big enough, you can scale out to a huge number of cores. And this is true of a lot of weather codes, for example, or the earthquake codes. All of them have this sort of situation where they're big domains, you can do a lot of work, and the send receive can be completely hidden behind the compute. And you'll get near perfect scaling in those sort of codes. And these are the codes that run at like 64,000 cores or whatever, huge numbers, because you're essentially hiding the communication. So how does that look on the call itself, right? So here I have an example of an MPI I send and an MPI I receive, which are basically the non-blocking ones. So you have a send buffer and you have the destination and you have a tag. The tag is actually now important because that is what, and there is a status, right? So basically the status is based on that request there. So you can basically check on the status. So, and that wait is not going to return till the receive is done. So that's basically the change in the call. And now going back to our deadlock example, now you actually don't need to do anything. You can make one of these calls. Remember, I mentioned that you can use any send with an any receive function. Like you don't have to match the blocking with blocking. You can have one non-blocking and the other one blocking. So in this case, I just made one of the sends from synchronous send to a non-blocking send. So then what happens is that the ISEND will return immediately and go to the receive line in the first process. And then the second task did a synchronous send, but since the receive from the first task will post, because now that it went to that line, that will pass, and then the receive will also pass. So that's kind of one way of fixing the deadlock too in the code. So that's the second fix that I have, and you can run it and check it for yourself, but we don't need to do that right now. So those were all the point-to-point routines. I didn't go into the one-sided routines, and basically there are mechanisms that let you write directly into memory on the remote node, which lowers the latency, and basically it's a one-sided write that gives you benefit on performance. But I haven't gotten into all those things. So there are a few hundred MPI routines. So we're going to barely scratch the surface today. We're probably going to look at 20 of them. So there's a lot. And if you go to the MPI standard, or actually go to the Livermore tutorial, you'll see a lot of options. So let's look at the collective routines next. So there are lots of different types. There's the synchronization types, where all the processes wait till they get synchronized. There are data movement collectives, like send receive data from all processes. Like for example, you might read something in one process and you want to broadcast it to all of them. Or there are scatter gather routines. There are all-to-all routines, where basically you might want to send data to all processes from all processes. This usually happens when you're, say, doing a transpose, for example, of a matrix. You might have to send the entire thing everywhere. So the collection, there are also collective computations, like reduction operations, like we saw the MPI sum reduction in the pi example. But there are all kinds of different options there. And then there are things that will do both the collective computation and data movement combined. Now, in this context, I want to say that some of the new networks architectures basically do have options to do compute on the network. So some MPI implementations now take advantage of that. So that like, some of these reduction operations might never hit the CPU. They might get done in the network and show up with the result. So all of these things basically are just going to enhance performance. So as I mentioned, basically on the simple Pi program, we had some already. We had a synchronization example where I was doing the barrier. So here the task will wait till they all get to this. Now let's look at some other collectives. So we'll start with, so all the examples are in the home parallel collectives directory. So we can run some of these. So basically, the first one we'll look at is the broadcast, which is, it's going to have some buffer array that is initialized in one processor, like say processor 0, wherever you want to do this. And you want to broadcast it to the rest of the processes. So the call basically has the buffer, the count, and then the type of variable. So in this case, these are integers. So we are basically using MPI integer. Source of the broadcast. So this doesn't necessarily have to be task 0. It can be some other task. And then the scope is basically the MPI com world, which is the communication communicator, sorry. So, and then I error is basically the error code in case this fails, you will get a non-zero error. And then you have the usual compilation and submission. So let's go here, go to the collectives directory. And we will, I should make sure I didn't change the compilers. Go to the instructions and make sure you use the compilers that are there, because the script has those compilers. So let me do that. You can change it in this case. And go to the collectives directory. And I'm going to compile the broadcast code and submit it. And it's already done. So, and you can see each processor is saying that it got the broadcast variable. Because I just put a print in every task. I mean, yeah, I just put a print statement. So remember, the same code is running everywhere. So unless you explicitly say don't run this on all the tasks or on a particular task, any code you write is going to be written, run by everything. So in this case, if I say processor X got the value, then it's just going to print out from every process. And it's not in sequence, by the way. So the output can come from processor 1 first and then 0 and so on. So don't depend on the output being sequential in terms of the tasks. It's going to all be mixed in. That was the example of a collective broadcast, but there are other routines. Like I mentioned, you have reduction routines. So in this case, I did a trick here to just find the factorial. As you remember, the ID, MPI ID starts from 0 and goes to the number of tasks -1. So I just add 1 to that and then do this reduction operation. So again, this is the local variable. Then the I factorial is the is where the output will go. And you can also specify which process that output should be on. So in this case, I'm saying the root is 1. Oh, sorry, this is the size. The root is defined somewhere else in the code. But basically, the size is 1, and because we are just sending 1 integer. And then instead of MPI sum like we did for pi, we are going to do MPI underscore prod, which is the product. And then we are sending it the output to this root process, right? And when the call is done, we're checking if we are on the root and basically printing out the factorial. So it's quite simple. So if you submit this job, you will see the output. So the next one is an all reduce. So remember there in the previous reduce call, there was a root process that it went to. But sometimes you want the result to be sent to all the processes. Good example is a lot of the fluids codes will calculate the time step based on the current solution field because the stability of the numerical method might depend on the time step based on the solution at a given time. So you're always calculating that time step and then sending it to all the processes. And sometimes you might be, that time step might be calculated at all grid points, and then you find some minimum or maximum of that. So you want it to go to all the processes. So these all reduces are kind of useful for that. So here we just do a random number and then basically send that out to do an all reduce and find the maximum overall. And there is actually a function that even lets you find out which task it's on. But in this case, I'm finding that explicitly, but you can actually find that out. And then you compile the code normally and submit it. So let me see, I heard a noise like, oh, it's another breakout room. Okay. Let's see. And output the maximum. Now, so you can do all reduce. So the next thing to look at is the data types. So there are a lot of data types already supported in MPI. So we looked at integer, but they're integer and float, but there's, characters, long ints, long ints, unsigned characters, float, long doubles, complex numbers, and so on. And both C and Fortran, basically. And you can also actually do user-defined ones. But remember that a lot of operations are, a lot of variables are already, data types are already defined. There's also a lot of operators in the reduction call that we had. We looked at prod and sum, but there's the maximum, there's a min, there's the sum, there's prod, there's logical operators. There's also the max lock and the min lock. This is what I meant by the location call. So now we know kind of all the basic routines that are needed to do an MPI code, like to actually use it to do parallel work. We kind of looked at the Pi program, but now I'm going to go to the next level of showing how you might have to break up the code, partition it to different processes, and basically map them to the different based on the ranks. And then we're going to see how you exchange data. We know the routines, now we have to see where that comes into play. And then some of the things that come into play are also like, how about if the workload is not balanced and so on. So there's all kinds of things to consider. So let's look at a simple example. We'll go back to the heat equation that we looked before. Remember in the OpenMP case, it was quite simple. We just said, take this loop and parallelize it, right? Here, basically, we are discretizing for the numerical solution, and then running for 3 steps again, basically. And I did exactly 3 processes here because that essentially covers all the different types of things that might happen for a 1D decomposition. So now processor 0 is doing 0, 1, 2, 3, 4. I mean, has the values for 0, 1, 2, 3, 4. Processor 1 has 3, 4, 5, 6, 7, and processor 2 has 6, 7, 8, 9, 10. And you might be wondering, okay, why are there these overlap points? Well, if you look at this discretization, right, on the time side, it's not a problem because the value at I just depends on the previous value at I. But on the spatial side, you see that I minus 1 and an I plus 1, right? So if you are on task 4 and you try to solve this equation, you won't be able to because you're on processor 0, which doesn't know anything about the rest of the data, right? Remember, in MPI, the memory is local to each task. So if you try to solve task 4, you will need I plus 1, which is 5, which won't exist. And same way, if you're on processor 1 at 3, you need I minus 1, which is 2, which you can't do. So what you do is you overlap and you solve 1, 2, and 3 on processor 0, 4, 5, 6 on processor 1, and 7, 8, 9 on processor 2. So that way, when you're at 4 on processor 1, you can get the 3 value, which it's in your array, and so on. Now, that of course means that you have to do some transfers, right? So the initial condition is fine, right? Every process can have its own initial condition set up based on the global index. Now remember, each task will have the same local indices. So it will go from 0 to 4 on each task. The only thing is the global index changes. So on processor 0, the global index is the same as the local index 0 to 4. But then on processor 1, the global index becomes 3 to 7 because remember, we are solving 3 to 7, right? And so on. So initially, you have the initial conditions at all the points. So you can solve 1, 2, 3 on processor 0, 4, 5, 6 on processor 1, 7, 8, 9 on processor 2, right? And then, and sorry, these are task IDs basically. And then you can do the data exchange from each task. So you send the value at 3 to processor 1 from processor 0, and then get the value of 4 from processor 1 back to processor 0. So basically, you start with the initial conditions, compute all the internal points, and then exchange the boundary point overlap points, and then go to the next step and do it again. So this also shows you where you can hide the compute. Hide the communication behind the compute. So for example, you could start by saying, oh, I'm going to compute 3 on processor 0, 4 on processor 1, and so on, and then send those, and then do the rest of the computations. So that way, the communication gets hidden. So how does this look on the code? Now this is the same kind of heat equation code that we had before. And basically we are doing setting the delta x, setting the delta t. Remember, all these variables are local to each task, so they will be there on each task. And you're doing the init, the comp size. You remember that was the size of the number of tasks basically. And com rank is the ID of the current task. And again, this was set up to run exactly with 3. In a normal MPI program, you wouldn't do this. You would basically do your own decomposition that is kind of dependent on the number of MPI tasks, and the task can be anything. You should write it such that it's like basically scalable depending on what input you give. So now remember, the local is going from 0 to 4, but we are now creating this global index and then setting the initial condition based on this, right? And then we basically do the update on the local 1 to 3. So the local 1 to 3 is mapped to the global on each processor differently, right? But remember, the initial condition already took care of that global piece. So you just do local 1 to 3 updates, right? And then once the update is done, you'll have to do the send and receive from each task. Remember, I'm not doing a synchronous send here, so the send will return, it won't block. But basically, you send from task ID 0, the value at 3, and basically, I mean, anyway, you can see all the transfers that need to happen. One other thing I want to mention is that after all this is done and you want to write the solution out, you now have a problem. Basically, your solution is actually also broken up, right? Like you have solutions on 3 different processes that need to be put together. So there are 2 options. If it's a small enough data set, you can send everything to one process and write it out. If it's big and it causes a lot of problems. For one thing is, it could be that it's so big that it doesn't fit in the memory on one task. Then you're in trouble because you can't send it to one processor to write it out. So then the options are, you write 1 file per core, which is what I'm doing here. Basically, I give a file name based on the number, the task ID. This function just converts it into a character. So if your my ID is 0, this will become data 0.dat and so on. So here I'm doing the dumb thing of writing 1 task per core, because then I don't have to worry about it. It's just going to write 3 files. There are, of course, other options, right? If you use MPI-IO, you could still write a single file, but then each task will write a piece of that file. So there are those options too. And if you look at most of the codes, most of the standard codes, they will do all kinds of options for IO. Like if you look at the weather code WRF, for example, it has the option of sending everything to processor 0. It has the option of writing task per, a file per core. It also has the option of doing parallel IO to a single file. So if you want a real world example, you should look at WRF. It has all those options. And it actually is a cool thing because it also has an option called quilting, which lets the IO happen from a subset of processes instead of all the processes writing. And that code scales to thousands of processes, basically. So going back to our code, let's compile it. I think it's, sorry. So it's in this domain directory. And I'm going to go to the particular compile line. And the MPIF90. You'll notice that I have this dash fixed form option. This is because the code is in a different Fortran format, the older format. So that's why this has been compiled this way. And let's submit it. Follow the commands. And if you do that, you will see, oh, I think I managed to do something weird with I think the cut and paste did something strange and created this weird variable. But anyway, there's already some executable there, so you should be fine. So you'll see that the output is out of sequence, like I was saying, like processor 1 is writing out first and then the others and so on. So there's that. But anyway, in the end, there's this solution set to file, and you see this data 0 dot dat, which is the value from data the first process. Data 1 dot dat is from the second, and data 2 dot dat is from the third process. So you see the output basically. Oh, something weird happened here. I think I might have messed something up in compile, but something weird happened. I'll have to go back and look at this. That's very odd. Let me compile this again. I need to write it explicitly. Okay. Also want to make sure I have the same modules loaded. That's odd. Okay, something weird is going on. I'll have to go look at the code. Or use a different compiler and see what happens. But let me show you the solution. It's odd. There's something strange with that compile, I think. So if you look at the solution, you should see something like this. I have to debug this probably for some other time. But basically, if you should see processor 0 with these values. So you have 0, 1, 2, 3, 4 with these values. You can see that the overlap points are correct, right? You have the fourth value here, 0.945 matches what you have on the other side. Like the, sorry, here on this side on processor 1. And then the third is also matching the third here and so on. So that's what I would expect. But for some reason, this last points were getting corrupted on that one. I'm not sure what actually happened. I'm pretty sure I've run this exact same code before. That's where the output came from, but I'm not sure what. Let's see if there's something. Yeah, this those numbers kind of feel like there was a leak somewhere. So I'll have to go back and debug it. But anyway, that's how it should look, the solution. Let's go back to this thing. So in terms of performance considerations when you do MPI job, so we already talked about overlapping communication with computation. So use non-blocking code, then you can hide the communication cost, and you can basically you can do different parts of the code of the domain while the communication is going on. Then the other thing is, remember the exchange that you're doing on the boundary is a surface exchange, right? So if you minimize the surface to volume ratio, the amount of communication will drop in comparison to the compute. So of course, if you can avoid communication in some way, that's also fine. There are some algorithms that let you do that. So talking about the asynchronous communication, basically the overlapping piece, there's actually also this thing where the network can handle all the communication piece, like I was saying. So you can offload it to the network adapter. So you can kind of do this compute, communicate, and then compute some more, and then complete the communication. So that lets you do some hiding. Now, if you want to know how your code is doing, there are profiling tools and tracing tools. So because you run a code, you don't know where you're spending all the time, right? So there's a lot of ways to figure this out. So, and they range from really lightweight like MPIP, which we'll look at today, to like tau, which collects a lot of information and gives you a lot of detail. And there's also the commercial tool DDT, which Alinea tool, which has a tool called MAP that basically also does this sort of profiling. These sort of tools are useful if you're trying to find performance issues. They can give you how much time is being spent in communication, and the level of detail varies with each tool. So this basically lets you identify bottlenecks and lets you overlap communication with computation wherever it's possible. So if you want to look at the MPIP example, let's go to the home parallel MISC directory, and there is this compile compile profile readme file, which actually tells you how to compile this code. But I already did this, and as you can see, we're doing the usual MPI compiler, but then adding this library. So -l MPI home lib, MPIP home lib, and then this library, and then some other libraries that kind of are needed for MPIP. What MPIP does is basically intercepts the MPI calls and then does the profiling. It's pretty lightweight in terms of overhead, and then it gives you a profile. So this is already done. So let's just submit the use the wrong. Actually, I don't need to do this, right? I just need to do reservation equals SI22 day 5. Okay, so submitted that, and oh, I'm curious if the data here is okay. This is a different compiler. Yeah, so you can see this is okay. So there's something weird with that compiler. I need to go back and check that. But yeah. So this, if you're wondering what I did here, I'm using the for the profiler, I'm using the OpenMPI compiler and running. So so you can see that the data 0, data 1, and data 2 now are like what I was showing you on the slide. Basically, you have these two overlap points matching these two overlap points matching these two. And then we have the profile also. So what MPIP does is, first thing, if you look at the output, it's going to have some additional info telling you that it's doing the profiling. So there's this piece of the output which is saying, this is MPIP with version 341 whatever build. And then it does the execution, and then at the end it says I'm storing the MPIP output in this profile. So if you look at the MPIP profile, this is a nice tool because it actually keeps track of when it was built, when this code was run. So we just ran it today. So you see the date, basically 10:06 on August 5th. And it tells you which nodes were used. Since this was a single node, you see the same node thrice. But if it was a multi-node, you would have the task assignment. So it's nice if you're debugging a performance issue, because sometimes the issue is not with the MPI. I mean, the code, it could be there's something wrong on the node, right? So you want a node list. And then it tells you the MPI time on each task. So it's the MPI percentage you can see is not much, overall 15%. And it tells you all the calls, right? Like the send receives and how much each of those took. And it actually has the size of the messages that are being sent. And it also tells you the timing for each of the call sites. So decent amount of information. The only thing you don't know is you're seeing all these in aggregation. You don't know like what sequence all of this happened in, right? So that's where you would need a profiler like Tau that can give you a lot more information. But as you can see, there's quite a bit of info here, right? So so you got the node list, you got the time when it ran. So if there are system issues, you can go back and correlate, oh, Lustre was not working that well that time, or oh, there was a network issue, so maybe that caused the problem. But you would know that from your profile. But it also gives you at the code level, like how much percentage MPI is doing. So one thing you can also see is it gives you the MPI percentage on each task. So sometimes if there is some imbalance, you'll see that like there's a lot of like some tasks are taking longer on MPI calls than others and so on. So you will be able to spot some immediate things. Or you can run this with MPIP at different sizes of your runs. Like say you have an MPI code and you're running it with 2, 4, 6, 8, 16, 32, 128, all kinds of processor counts. You want to see what's happening with the MPI percentage. Like if that starts growing, then you know that the problem either is too small or your communication is not scaling in some way, and you have to go figure out why that's happening. Because if that MPI percentage goes off to like say 50, 60%, then your code's basically very inefficient, right? Because you're spending 60% of the time communicating and only 40% of the time doing the actual calculation. There's something wrong. So there's that. So as I mentioned, we didn't look at everything today. There are lots of complex routines that can use derived data types. You can have user-defined reduction functions. You can have groups of processes in different communicators. You don't necessarily have to put all the tasks into all the whole into the communicator. We didn't look at parallel IO at all, but there's parallel IO routines that let you write out single file, but from all the processes. So you can basically write different parts of the file from different tasks. We didn't look at the one-sided communications, which can do the remote direct memory access that I was talking about. And this is what helps you lower the latency even more in terms of network. So the MPI 3 standard has over like 400 routines, so you can look at that. I threw one code in there which has 2 bugs. Again, this is not something you have to do today, but you can poke around and see if you can find these bugs. But basically, there is something there. So that kind of ends all the info about MPI routines and how you can decompose a problem and solve things. Let me just quickly take a look. Okay, we don't have anything, so let me go back to this. I'm going to finish with a couple of things. One, a specialized MPI implementation for GPUs, because we didn't even talk about GPUs today, but there's actually special implementations. And then I'll talk about some binding and kind of task layout things that you have to keep in mind. Again, that becomes very important when you have nodes like Expanse, where you have 128 cores. The most likely thing is you're not going to be running with all 128 tasks on the node. You might run with 8 tasks or 16 tasks and do threads. Or like, you might do 32 tasks and 4 threads. Like, for example, the high performance, implementation, highest performance of WRF implementation comes with a hybrid run, like once you start get to large core counts. So there's always hybrid runs that you can do. But then there are considerations of how you lay out those tasks. But before that, I want to talk about MVAPIX to GDR. And OpenMPI also has implementation that does GPU direct. But basically, this is a specialized MPI that works well on the GPU nodes. So I'm going to start off by kind of showing how one of our older systems, Comet, had a node layout like this. Remember, I was showing you the CPU architecture basically with 2 sockets, right? Now, when you have GPUs, the GPUs can be all tied to one socket, or they could be split. Like on Comet, what we had was 2 GPUs on each socket. Now, there is no direct connection on Comet between these GPUs. The GPUs on the same socket could talk to each other directly or PCIe, but they could, GPUs on the different sockets. If you want to talk to GPU 0 from 2, you have to go through the CPU across the QPI and back down to GPU 0. So that can add a lot of overhead on a GPU code when you're going through the CPU for communication. So what the GDR does is there is something called GPU Direct RDMA, which lets you basically access the memory of another GPU. Now, if your network card is on the same PCIe bus, you actually don't have to go through the CPU to use the network. You can go straight through the network from the GPU to the network to another node and to the GPU there. So, of course, that's possible at the low level, but then your MPI needs to be aware of that, right? Otherwise, the MPI will just say, oh, I need to transfer from the memory buffer on this CPU to the memory buffer on that CPU. It doesn't know about the GPUs. So basically, that would involve like a lot of overhead. And then actually for GPU codes, it was going to affect the scaling quite a bit. What GPU MVAPIX to GDR and also the excuse me, the OpenMPI version that also has a GDR version lets you do is basically bypass the CPU on the transfers, and the memory and the MPI communication is happening GPU to GPU. This is kind of the P100 architecture of Comet. Basically, what I'm showing is the topology output for each node. So you can see that GPU 0 can talk to GPU 0 itself, right? But then if it's on the same socket, it can basically go through the same PCIX. But if it's on a different socket, it needs to go through the SMP link between the CPU sockets, which is the QPI in this case. So when you do latency checks, you'll see that if it's latency between GPU 0 and 1, you have 2.73 microseconds. But if you go from GPU 1 to GPU 2, which are not on the same socket, you get 3.13. So there's quite a bit of latency overhead. Same thing, internode, there's a difference between which GPU you go to, even with the GPU direct implementation. Now, on expanse, it's a little different. So we have 4 of these V100 GPUs. They are all basically connected with NVLink. So so you don't actually have to go. So if you look at the topology of the expanse GPU, you don't actually have to go over the CPU socket, the link between the CPU sockets. You're basically just using the NVLink between all the GPUs on a node. So so if you compare basically now the latency on Comet and on Expanse, you can see on Comet, there were different curves depending on which GPUs you were using, right? But on Expanse, all the curves are basically the same. And not only that, the latency is much lower too. We can look at, it's like 1.5 microseconds. So things are a lot faster on Expanse between the GPUs on the same node and even on the remote, right? So if you do the intranode benchmark for the bandwidth, you'll see it like basically on Comet, if the GPUs were on the same socket, you get pretty good bandwidth. It goes up to basically what's that, like almost 13,000, so 13 gigabytes per second. But when you get to do this between GPUs that are not on the same socket, it does okay to some extent and then just flattens out. And this is the limit on the basically going through the CPU. That's the issue there now. Whereas if you go to Expanse, you can see that doesn't matter which combination you use, you end up with basically the nice clean bandwidth curve, and it's all at a very high bandwidth. It's like 40 gigabytes per second. Similar thing when you go off node. I don't have the numbers, but you can basically you can imagine it's the same thing. So, okay, the last part of the talk is basically on the hybrid MPI OpenMP jobs and like how you want to run this on Expanse. So I'm going to be basically talking about the IV run scripts which Manu developed at STSC. And this will be in your path if you do module load STSC. So going back, let's recall that processor architecture. So you have the 8 core complex dies and the CCDs going through the IO die and so on, right? And then in each core complex, there are 2 core, core complex die, there are 2 core complexes, each with 4 Zen 2 cores, which are sharing an L3 cache, right? So when you're laying out like a hybrid job, like say you have an MPI like 32 MPI tasks on a node and 4 threads per task. To get good performance on the shared memory part, it might be good if you just put all of them on the same cache. So you put 4 threads on the 4 cores that are sharing the cache. So this requires basically control of where your tasks are landing, right? Because this is quite important from a performance standpoint, because remember the memory also gets partitioned into different NOMA domains, right? So on Expanse, we have 4 NUMA domains per socket, and you have 2 memory channels associated with each of the NUMA domains. So when you're laying out the tasks, you don't want to be going across things and ending up having to get the additional latency. Like, since we have 4 NUMA domains and each logical quadrant is a NUMA domain, and the memory is interleaved on the 2 memory channels there. And also, one of these NUMA domains is where your network card is, by the way. So there are different ways of doing this. All the MPI implementations have affinity options. So you can, for example, in OpenMPI, you can do MPI run with 32 tasks, and these MCA PML options, these are basically more to do with the communication. But there is this -- map by L3 cache option. So it'll explicitly map it so that each of the MPI tasks is on a different L3 cache, and then the threads will be basic. So if you have 4 threads, they'll end up on the same L3 cache. In Intel MPI, there are options to kind of do MPI pin domains. I think with the newest versions of OneAPI, this changed, but with the older Intel MPI versions, they had these pin domain options where you do OMP called compact. And Intel MPI is smart enough to say, oh, you have 16 threads and you have 8 tasks. So then it's going to lay it out in a fashion that is sequential, but giving room for the 8 threads. Sometimes the application itself has pinning options. Like an example is NAMD, which is a molecular dynamics application. It does very specific layout options. So here I'm combining the two, by the way. What I'm doing here is saying MPI run -NP8. I'm saying Mac ranks with 4 tasks per node, right? So that's one thing. So you will have 4 NAMD tasks, but then the tasks themselves are laid out according to this structure. Basically, NAMD has this option to set CPU affinity, so it will pin things. Then it also has the option of saying, hey, how many threads do we have on this each task? So here we are saying 31, and you might be wondering why not 32, because you have 32 cores per task available if you do 4 tasks. The reason is because NAMD has the option of having dedicated communication threads. So all of these are to kind of prevent the regular compute task getting overloaded with communication aspects. So you have a dedicated set of tasks for doing communication. And then last thing is NAMD lets you actually lay out the tasks according to the core ID. So here what we are saying is, hey, use core 0, 32, 64, and 96 as communication threads, and then use the rest for compute. And we are also explicitly saying the first compute task will have 1 to 31, second will have 33 to 63, and so on. So you're kind of laying out explicitly what you want. Now, if you're writing your own code, you could be doing this yourself also explicitly, because both MPI and OpenMP have options to kind of do this from within the code. So then, but sometimes that's not an option, right? You could end up with a code that you didn't write. It's a hybrid code, but you need it to be set up correctly. So that's where IB run and affinity come in, basically. So we've tried to make it easy so that all you have to do is IB run and the executable, or like, with affinity, just IB run affinity and give it some hints and the executable. Right. And the affinity options, there are lots, right? Basically, you can scatter, that will scatter the ranks across all NUMA domains in a cyclical manner. You can do scatter CCD, that will scatter the ranks across all the CCD domains in a cyclical manner. You can do scatter CCX, which will scatter across all the CCX domains in a cyclical manner. So remember the NAMD situation where, or not the NAMD, but the first OpenMPI example where I did 32 tasks and then mapped by L3 cache. You could achieve the same thing by doing IB run and saying scatter CCX. So that is, let me go back here. Okay. So that would be the equivalent of what we did there with the MPI option. Here you could just do IB run, affinity, scatter CCX, and then run with 32 tasks. And it will put those 32 tasks on different CCXs because you have 32 CCXs on a single node. You can also scatter with a block size. So you can kind of achieve the same thing if you want with setting up different block size. And then it will just go in sequence on the tasks. So there's so many different options, basically. So in terms of trying to make sense of this from the diagrams, what I did is had the NUMA domain, because remember we have 16 cores in each NUMA domain, right? Remember 2 CCDs in one NUMA domain. So so you have basically 16 cores in each NUMA domain, which share like 2 of the memory channels. And then what we are doing is saying that 4 of these are in one CCX. So that's how it's laid out. And this is not a physical representation. This is more for you to kind of figure out how things are being laid out. Let me see if I heard something on the. So there was a question about like the length of access on the accounts. I have to actually check on when that ends. So the example IB run options and layouts that we are going in right now, we will try different things. So first thing I'm doing is 2 nodes. Saying CPUs per task is 1, so it's a very serial, not serial, but single-threaded MPI task. And then number of tasks per node is 4. So you have a total of 8 tasks in this case. So basically, I'm doing SRun, right? If I do SRun, it would have been 8. So here I'm just saying IB run and this executable. That's it, giving it no option. So by default, it's going to scatter cyclically across all of them. So that's why you will see the first NUMA domain 1 task, and then goes to the next NUMA domain another task, and so on. So that's how it will do it over 4 nodes, so that it's kind of evenly spread out across the 2 nodes. This will basically give you the maximum memory bandwidth for each task, right? Because each task is getting 2 channels here. And then say you have 6 tasks per node, and you say scatter in block 3. So then it's doing this per NUMA domain, but it's scattering with 3 tasks on each block, right? So then it'll do T1, T2, T3, T3 on the first NUMA domain, T4, T5, T6 in the second, and so on. So then it's kind of laid out that way. The third option I'm showing you is basically CPUs per task is 2 and n tasks per node is 6. So now you have threads, yes, doing 6 tasks, and then you do a scatter with the block of 3. Then what's happening is now it puts 2 of the threads on the same CCX and basically cycles through again. So now you have T1, T2, T3 are 3 different CCXs, right? And so on. So there's that. And then you could do a scatter at a CCD level with a block of 2, then it'll put 2 tasks on each CCD and go on, right? So you have a lot of control on how the tasks are being laid out, basically. And if you do a scatter CCX, then it'll put 1 task in each CCX and cycle over the NUMA domains. So now what we are doing here is doing one node and n task per node is 32 and CPUs per task is 4. So if you notice here, basically this is a LinPack run which is used basically to benchmark the systems. Usually this is the number that's used to calculate the top 500 ranking of a machine. So I'm doing IB run affinity scatter CCX and XHPL, which is the executable's name, a variable that has executable's name. So I just said scatter CCX, and basically now it's put 1 MPI task on each CCX, and then the threads are on 4 threads on each CCX. So you can see that the master task is kind of 100%, and then the threads are basically a little bit below because I caught it at a time when it was not fully utilizing all the threads. But you can kind of see the layout now, right? And all 128 cores are busy and they're done correctly. Now, if you had not used affinity or scatter CCX and then said, say, if you just said n task per node is 32 and didn't do the CPU per task, what you would end up with is this task here would end up with all 4 threads on it. So you would see this in red, like one would be in red, 5 would be in red, and so on. So you would basically end up oversubscribing that core, and your performance will be pretty bad. So you might not see the improvement due to threads because you will not see the improvement due to the threads because the threads got pinned to the wrong cores. So it's quite important to lay it out correctly. So again, this is a different way of looking at it. Basically, what I'm doing is looking at the processes and also looking at the threads associated with that. So you can see that the task ID, the process task ID is the same for all of these threads, right? It's because these are all spawned from this master process 82667. And then they're threads, right? So the 4 threads, 0, 1, 2, 3, you can see there. With basically associated with one task, and then the next task is 82668. These are not in sequence. This is gone off into the 40s in terms of the core IDs. But you can basically see that we are not oversubscribing. We are basically laying out correctly. So to basically summarize what's there on Expanse in terms of binding options. So since the AMD processor on Expanse is laid out so that you have 4 NUMA domains with 16 cores each, and with 8 core complex dies per processor with 2 core complexes per CCV. So the 4 cores in the CCX share the L3 cache. So that's, you keep that in mind when you're laying things out. For the hybrid OpenMP and MPI, or even MPI and pthreads codes, it's important to lay out the task correctly. So the binding is really important in such cases. Remember not to oversubscribe, basically. There are lots of things to keep in mind in terms of oversubscription. One is the binding, but there's also, like, when you launch the tasks, make sure you're setting the CPUs per task correctly. Because otherwise, if an MPI task gets bound to a core and it doesn't know that there are threads with associated, it's going to bind all the threads to the same core. I want to kind of end with a bunch of references from Livermore. Like I said, these tutorials are way more detailed than what we have, just because from the time constraint perspective, I didn't go into all the details. There's MPI for Python, if you're interested in that, MPI for Py. And like I said in my code porting talk, when you do MPI for Py, you have to be careful to build the MPI for Py with the MPI that you're going to use on Expanse, because if you do a conda install, it's going to pull in its own MPI, which won't be using the high performance network. And then there are user guides for OpenMPI and MVAP-H2. I just want to show you something because this can get very detailed. That's the user guides. So if you click on the full user guide for MVAP-H, for example, you'll see we just scratched the surface in terms of what options are there. You can kind of see there's the whole layout information and stuff. They have some feature information. But then if you scroll down, you'll see this is the build information that you don't have to worry about because we did the build. But then then starts all the layout kind of options that MVAP-H itself has, right? Let me go scroll a little bit more. So yeah, so yeah, you can start here. Basically, it has binding policy things that it can do to kind of, again, lay out within MPI. See, remember, I showed you IB run, which is doing it from a system level, like in terms of we find the info from Slurm and do it, but you can do it from MPI too. So that's what I wanted to kind of show here. So there's all these placement options and CPU binding policies that you can do. And it does make a difference in terms of how you bind. You can, and they have some performance impact of basically latency and so on. They also mention Limit, which is built into MVAP-H2. And they also mention some other things called XPMEM and everything. So those are kind of built in that you don't have to think about. But what I want to show is that there are other things that involve, like how you use the network, that I didn't go into. But they actually have options to kind of set the thresholds. So let me scroll down and maybe show you some examples of that. Let's see. Go. Yeah, so you can see, like in the shared memory tuning, there are thresholds. Then there are thresholds on the collectives, on the message sizes and everything. let me go on a little bit further. I'm looking for a particular example. There's also debug info that you can print out. There's checkpoint flags. So you can see the CPU mapping flags, the CPU binding flags. There's the hybrid binding flags. So this is for the MPI plus threads. So whatever we did with IB run, you can also do it with MPI run, MPI MVAPIC options, basically. There's this enable affinity option. But then you get into all these options that are for the network and everything. So like the number of ports and if they're multi-rail, like how do you want to share the two rails? Then there are thresholds for these sharings. And then as you go further out, you'll see there's thresholds on the IB side, like which protocol you want to use. And then you will also see that there'll be some shared memory options on what you want to do. So you can see lots of details. So once you start figuring out like from the profiling, like where your message sizes range from and like kind of where they fall, you might want to go back and look at the MPI and see, hey, like at this message size, is it better if I change some of the flags? Because sometimes what happens is, not sometimes, MVAPIC and OpenMPI both, like when you do collectives or when you do point to point, there are different, especially with collectives, there are very different algorithms depending on the size of the message. Because you can do some things faster if the message sizes are small, because you can use the network differently. So there are thresholds where this changes within the MPI, and these are preset tuned for particular machines. Like so on Expanse, the MVAPIC to install already kind of is aware that this is an AMD processor and it has its tuning set up for that. But that is set up for a very generic case, right? Your particular application might have a different profile in terms of the sizes of the messages you're sending or whatever. And in that case, you might want to go and find out, hey, I might be right on the threshold. And sometimes one algorithm does better than something else, and you can switch it. And then even all reduce, for example, there are different algorithms of doing all reduce. You can do different all reduce in different ways. And again, those can be changed with flags. And you'll have to play around to see which one works better for you. So lots of different options, basically. So keep that in mind. And the one other thing, I don't know if I have an example. I mean, I was reminded of it because we had the threaded example in MVAPIC, but let me see if I can find one in my own account that shows how to do this for pthreads. So today we didn't talk about pthreads at all. We were talking about MPI and OpenMP, but some codes do threading using pthreads. And the problem with that is with OpenMP, there are like explicit flags you can use to kind of set environment variables to bind things. But with pthreads, there's nothing like that. You either have to bind them internally in your code, being aware of what's going on, or you will have to bind the threads after they're launched. And this can cause a lot of performance issues if they're not bound. And one such code is RaxML, and I'm actually looking for an example of that. And so that I can show you. So I'm trying to figure out if I can show you an easy example. Otherwise, I'm going to probably go and show you the script itself. We have a script to kind of deal with the affinity. Apologize, I should have actually gotten this set up first. Okay, let me just show you the script. I think that might be. So basically, we have this script called Slurm affinity prod that again Manu wrote. Basically, what it does is it binds the p-threads within an MPI task to the cores that are given to you. So so what you have to do is basically launch your MPI job with the p-threads, let the p-threads go wherever they go, and then after like a so in the script you can basically wait a few seconds and then do this affinity that basically takes the name of the script, name of your executable, to go find the threads, and then does the right affinity based on what. So you have the name of the binary, the number of MPI tasks, and number of threads, right? And then it's finding the number of tasks based on the Slurm task per node, and then the number of threads using the CPUs per task. So all you have to give it is the name. And then it will say, oh, yeah, this code is supposed to have, 4 MPI tasks and 5 threads each. Now, when the job launches, it's going to throw those 5 threads all over the place. And sometimes what happens is 2 of the threads end up on the same core, and then you get really poor performance. That's essentially how we found out that, okay, we have to go write something to change this. So this affinity script will basically go and realign the p threads to the right cores. So that's one more thing to keep in mind, and I think that's what I mentioned here, the Slurm affinity prod script. I was hoping I could show you in the script, in a RaxML script itself, but anyway, it's another affinity thing that you have to keep in mind. So I think that pretty much ends what I wanted to talk about today. The main thing to keep in mind is that with OpenMP, everything is shared memory. You have to, you can bind tasks using the proc bind option. And you can, there are affinity flags in OpenMP too, like where you can lay out the threads the way you want. With MPI, again, the task can be bound to the cores. Just make sure that if you're doing an MPI OpenMP hybrid, you don't bind all the threads to the same task, that the same core that the MPI task is using. So you have to make your setup aware that basically either use IB run to lay it out correctly, or if you're using the MPI way, use the MPI flags that let you do it. So we saw the flags for OpenMPI and also for MVAPIC, so you can go set those. And then if you have a combined MPI pthreads code, use this affinity script. I think that that's good to remember. I think I'll stop at this point and